All right, so we're going to get a little introduction of the next topic. The next topic that we're looking at for integrating applications is something called volumes with known cross sections. This is different than the volume that we just spent several days covering. We are no longer taking a region and revolving it around an axis. Instead, what we're doing is we're starting with an enclosed region. So you'll have some sort of base. We call it the base of the solid, where we're going to know definitively what is that shape. Is it two functions that are intersecting to create the shape? Is it a kind of known shape? And then what's going to happen is we're going to slice that, and each slice is going to be a particular geometric shape. So what you're going to think of, and the reason I have my face in here today, is you're going to think of it as your base as being a flat region. And then you're going to think of these cross sections as coming out through the page. Let me do it like this so you can kind of see. Coming out through the page. Ooh, and coming up and creating different shapes. I am going to show you some Delta Mathis because my prop maybe isn't the best. But again, the idea is that I am taking something that is flat, a flat base, and I am taking these shapes and I'm pushing through the base and creating like a layer of cross sections that are going through. So when I do this, one thing the problem has to tell us is what shape is kind of coming out of the page at you. And there are very specific shapes that the AP will use. So you'll have something like a square cross section where you're going to have one square after another that are popping out of the page and creating this three-dimensional shape. You'll have triangles where you'll have a triangle where on the base, the edge may be like the hypotenuse of the triangle, and that those triangles are coming out of the page. It could be semicircles that are coming out of the page and creating this three-dimensional figure. So these, a lot of times students say that at first these seem like they're more complicated than the volume with revolution, but after do a few, then they change their tune and say, you know what, actually this like makes a little bit more sense. We're not quite as reliant on the picture. It's hard to visualize at first though. So when we do these, what we're going to need to do is figure out what's the area of each of these slices. So as I'm slicing it into triangles or slicing it into squares, what's the area? If I can come up with a formula for area and integrate it, then the integration will accumulate all these slices and find the total volume. So what you're going to see, and here's my formulas down here, is you're going to have the slicing start and stop at A and B. So your boundaries again are kind of that start and stop. And then your A of X is going to be how do we represent the area of that slice, of that cross section. Most of our problems will be perpendicular to the x-axis. So as we draw them, and I'm going to show you examples of this, we're going to see that slicing happening perpendicular to the x-axis. If they are slicing in perpendicular to the y-axis, which is not nearly as common, you would actually have everything turned sideways and it would be in terms of y's. So the thought process, and then I'm going to show you some visuals, is first you want to figure out what does the base of the solid look like. So are you looking at a couple functions and creating a region? Then you want to picture that solid as coming out of the paper, like it's giving you like a 3D effect, which again, I've told you before, I'm not good at visualizing, but I think when you see some of the software ones, it makes life a little bit easier. On your picture, and your picture is just going to be a flat 2D picture, you're going to label one side of the shape that's coming out of the page. So it could be the side of the square or the side of your triangle, or it could be the diameter of your circle. Once we know that, we're going to put it into our area formula. So I have all the area formulas down here. Let me move myself so you can see all of them. And then you're going to integrate your area from the start to the end of the slicing. So the common formulas, and this is like in order of how they show up, the most common and the easiest is that we're slicing it into squares. The next is circles. Actually, you probably won't see much with regular circles. Instead, you're going to see more semicircles. So you're going to see almost like arches coming out of the page. Here's your formula for semicircles. You're going to take that diameter length and square it and multiply by pi over 8. Your equilateral triangle, where the one side of the triangle is going to be laying along the edge of that base, is your formula is that side squared and then root 3 over 4. And then an isosceles right triangle, where the hypotenuse is laying along that side, would be in the formula the hypotenuse squared over 4. What you'll notice is we always have that length squared, no matter what we call it, and the only thing that changes is the coefficient, which makes this process nice because once you figure out like your basic square, you can actually tweak any of these other ones just by changing the coefficient. So let me show you some visual examples. So in Delta Math, here's some examples, and I love that they show this like slider piece. So R is your base. So this is your region right here. And it's formed by taking the functions e to the x minus 1, which is obviously the curved one, the exponential growth, and 4x, which is the linear one, and finding that area that is present. And we've done a lot with these things. We've found area, we've revolved it, but now we're doing something a little bit different. What we're going to do is we're going to slice this into isosceles right triangles, where the leg of the triangle is actually laying on the region. And then we're going to use our calculator to figure out the volume. What I want to show you here is just how the slider works. So as we start this process, you start to see these little triangles show up. And you'll notice the bigger the region is, the further it is from those two functions, the bigger the triangle that's formed. And so as I keep putting slice after slice after slice of triangles, I create this three-dimensional image. So that's what you're finding. You're finding the volume of this 3D image. Let me show you one with different shapes. So this one is a rectangle. I actually don't do a lot of rectangle ones. I do more squares because I think the AP test likes squares better. So you have your function x squared minus 2, which is your parabola, the horizontal line y equals 3, and the y-axis. And that's giving you my region. And we are going to slice it into rectangles. So you can kind of see, where's my, there it is. So here's my rectangles. And we're slicing this region starting at the y-axis. That's why I didn't start for a while, and creating a three-dimensional image. This one is a square. This is probably the most common. It's also the easiest for students to understand. So we're taking this base, go back here. Here is my base. It is formed by looking at the functions natural log of x and 1/3 x minus 1. So this intersection right here, that area. And then we are slicing it into squares. And then this will be what it looks like as those squares fill in. You can see you get bigger squares as the base is bigger. You get smaller squares as the base is smaller. It's kind of cool. I want to show a circle one. If I can find a circle or lots of rectangles. It's funny, Delta Math does a lot of rectangles. AP Test actually does more semicircles. Give me a semicircle. Maybe it doesn't want to give me a semicircle. Here's another triangle one. So you can see that as the triangles form, giving me that base. Semicircle, just took a while to find it. So with this one, so my base is the cubic x cubed minus 1, the horizontal line y equals -3, and the vertical lines x equals 0 and x equals 2. So we've got my x equals 0, x equals 2, my horizontal line, my curve. So this is my base. I kind of wish they would color that in a little bit. This is my base that's going on here. And we are going to slice it into semicircles. So let me show you how these circles form. So here's our first couple circles at the very beginning of the region. Starts out very small, and then as this base gets larger, my semicircles increase until you get a three-dimensional figure. This one's kind of funny because it looks like it's come out of the page, all created by a bunch of semicircles. It kind of has this like curved look to it. So I wanted to show you that one. I wanted just to show you some pictures. We're going to get in class and do some examples with it, but I really wanted to make sure you were comfortable with what are we actually finding so that when you're in class, it makes a lot more sense to actually find it. All right. Thanks for watching.